This is where we're going to start, the ideal gas law. The ideal gas law is for one set of conditions. I call it Piven for short. Notice that this is the computation that accompanies the ideal gas law. There's going to be 1, 2, 3, 4, 5 variables as written. And the ideal gas law is exactly that. It's a way to calculate ideal gas conditions, and note the word ideal gas. That has very specific units. Pressure must be in atmospheres, volume must be in liters, N is moles, there's no other unit for that, and temperature always must be in Kelvin no matter which gas law you're using, whether it's the combined, the ideal, Lusak's, any of it. Always Kelvin, 273 plus degrees Celsius. And that'll change it into kelvins, because they'll always give you the temperature in degrees Celsius, and you have to do the math to get it into Kelvin to put it into any of the gas laws. Now, why specific units? Because none of the other guys were specific units. They were just the same. You had to have the same in order to do the algebra. But this one has very specific units. How come? Well, R is a constant. So R is 0.08206 liter atmospheres per mole Kelvin. R actually dictates what units your pressure, volume should be in. And not only that, but it cuts it down to this computation being a mere 4 variables instead of 5. Now you're dealing with only 4 variables because R is a constant. Alright, what's it used for? It can be an equation of state for a gas. That means its condition at a particular point in time. A particular state of a gas is described by its pressure, volume, and number of moles. Applies best at pressures less than 1 atmosphere, because that's when gases act ideally, and you can use the ideal gas law. Real gases approach this ideal behavior at low pressures and high temperatures. And again, low pressures because at low pressure the gas particles are really spread out and there will be no attractive or repulsive forces. And at high temperatures they're moving so fast that there will be no attractive and repulsive forces. Ideal gases are hypothetical, but the math actually works pretty well. So we go with Piven for the ideal gas law. Something else I want you to know about Piven, it can actually be used for changing conditions also. If you have a set of conditions versus the second set of conditions, what's the only thing that's the same in both conditions? Well, R is a constant. It's not going to change. That means this one becomes P1 V1 over N1 T1, and this one becomes P2 V2 over N2 T2. Well, if R is equal to this and R is equal to that, then guess what? For a set of changing conditions, you can actually use the Piven, put all the stuff in that's in the problem, and whatever's constant, hold it out. For example, let's say you're reading a problem and the number of moles remains constant. Well, you're going to be able to remove this variable from the equation, and what do you got? You got the combined gas law. What if it's a problem that has pressure and number of moles constant? You're going to remove that and you got Charles's law. So Piven can be used also, and Piven is actually the other ones combined. Alright, so here's an example. Hydrogen gas behaves ideally at 0 degrees Celsius. It has a volume of 8.56 liters at 0 degrees Celsius and a pressure of 1.5 atmospheres. Calculate the number of moles of hydrogen gas and its mass. All right, first off, notice there is only one set of conditions. They are not changing from one to another. They are merely asking for N given the other things. So this is going to be Piven. Okay, given in the problem, I have a volume which is 8.56 liters, and it is in the right units based on R. I have a temperature which I need to change to Kelvin. And I have a pressure. All right, I'm going to use Piven. This is a set of one set of conditions, finding N. And I'm just going to fill my numbers in the right spots. 1.50 atmospheres, it is the right units. 8.56 liters, it is the right units. My R is 0.08206 liter atmospheres per mole Kelvin. And my temperature is 273.2 Kelvin. Plug it into your calculator and you get a N, which is number of moles, of 0.573 moles, 3 sig figs, of hydrogen gas, and multiply that by its molar mass, and I get 1.16 grams of hydrogen gas. Done. Example number 2, ammonia gas with a volume of 7 at a pressure of 1.68 atmosphere, compressed. Remember, gases are compressible. So you're taking 7 milliliters and shoving it into a 2.7 milliliter space. Constant temperature. What is the final pressure it's asking for? So here's a couple of things I want you to know before we proceed. This is a change in conditions. Also note that the temperature is constant, and so is N. Nowhere in this problem does it say they add more ammonia gas to the container. All they're doing is changing from 7 mils, the same number of N, or same number of moles of ammonia, from 7 mils to 2.7 mils. So temperature and N are constant. Right, so here's what's given in the problem. I have a volume, and I have a pressure. I have a second volume, because they change it, and they're asking me for the second pressure. So I'm going to use Piven for changing conditions and show you how this can be so simple. Piven for changing conditions is this. Which I showed you a couple of slides back. You have a changing conditions for Piven. Whatever is held constant, remove it from the equation. My number of moles and my temperature is held constant. So remove it from the equation. Now I have a mere 4 variables here. 3 are in the problem, so fill them in the right spot. Again, for the gas law guys, which this is technically Boyle's law from a previous video, for the gas law guys you don't have to have specific units, but they have to be the same in order for the algebra to work. Now I don't care if you put your numbers in first and then do the algebra, or rearrange the equation. It's purely your comfort zone. Either or, it doesn't matter to me. You get the same answer. The second pressure, after smooshing it down, pressure goes up. That correlates to Boyle's law. Now here's a little picture, that a little analogy, if you will. Let's say you have a tank of gas particles. Now, again, pressure is measured by how often these little particles beat against the side of the container, right? And if they're pretty spread out, they're not going to beat against the side of the container that much. So this is technically a high volume, but a low pressure. If you squeeze it down, suddenly you have a low volume, but those gas particles are going to really bang up against the side of the wall a lot more in the low volume. So you are going to end up with a high pressure. This is what Boyle said. It is the only one that has an inverse relationship. Opposite to. Next example. Diboron gas, pressure 345, temperature, volume. What's the new volume? So this is a change in conditions. I can spell. Let's see what's held constant. I have pressure, temperature, volume, the first set of conditions. Looking for new volume, temperature change, pressure. The only thing that's held constant is the N. They do not add more gas to this sample, so constant number of moles. Alright, so given in the problem, I have pressure 1 being equal to 345 torr. Now this is changing conditions. This is not going to be using the one state Piven. That means my units don't have to be specific with the exception of temperature, but they have to be the same in order for the algebra to work. Be careful of that. Your temperature always has to be in Kelvin. I have a set of second conditions after the switch, after the change. They increase the pressure. They increase the temperature. And they're asking me about the volume. So this must be in a flexible container that the volume changes. Maybe a real thick latex balloon or something like that. So I'm going to assume that since, well, actually you can't make too much of a judgment because not only are they changing pressure, they're also changing temperature. So I can't go with Boyle's law, who said that if pressure goes up, volume goes down, because I'm not sure, because the temperature for Boyle's law is always held constant. It's not being held constant here, so I can't make a hypothesis. I'm going to have to just do the math and see what I get, see if it's logical. Alright, so I have, well, you got a couple of varieties. Here's the combined gas law, or technically it's changing conditions Piven without N. Whatever, you get the same thing. Again, whatever floats your boat. If you want to rearrange for V2 first, that's fine. I'll put in the numbers. Since there is no R, I can leave the pressure in torr. They don't have to be specific units, but they do have to be the same units. Now I'm relatively lazy, so I put my numbers in. Because you got a lot of 2's and 1's floating around. Rewriting it, something's going to get messed up. Now here's what I do. I multiply the entire side that's complete. So I multiply this entire side together, and then I divide by the product of these two guys. So multiply the 3, divide by the 2, and you get your answer. But this is algebra, you should know this. So notice my volume did go down. Pressure went up, volume went down. So it did kind of follow the Boyle's